Assalamualaikum and hi to everyone. So in this video, we continue on the previous video on chapter 3 regarding the operation or the process concept. Okay. So in this section, we go through the process representation by the Linux. This is an example. Okay, you can see at that diagram, we have 3 parts. Okay, so the process here is referred to control block. Okay, we have 3 block here. Is based on the Linux operating system. So based on the example, we have the state. So the state, okay, the long state of the process. This one is the process. So some of this field under the process, including the long state, is referred to the state of process. The struct scheduling entity, SE refer to the scheduling information, and then we have the struct task underscore struct. This one refer to the process parents. It look like a tree. The structure, okay, the structure on the control for the operating system is represented in the C structure. So you can found under the Linux /schedule.h header. So include the file in the kernel source code directory. So this structure contains all the necessary information of representing a process. Okay, information on the process. So it will include the state of the process. Okay, for example, we have long state of the process. Okay, that part. The scheduling and the memory management information, list of open file and the pointers to the process parents, and list of its children and siblings. So it looks like a tree. So it has parent, and then under the parent we have the children, and then we have the sibling. Okay. So a process parents is the process that created. Means the process that created it. Okay, and the children is based on the parents. Children are the process or any processes that is created by the parents. So the sibling are children with the same parent process. So some of these field will include this structure. Okay, long state structure identity. Okay, that's why here we have the children, list head children, and then we have the parent here. So this process, parents process, and then this one is the process. Okay, this one for the parents. Okay, this one for the children, and this one for the open file. Okay, so basically it is include the process itself that being executed. So based on this example, the state of a process is represented by a field long state in this structure. So within the Linux kernel, all the active processes are represented using the doubly linked list of a task structure. Okay, you can look based on the block. Okay, this one is the active process, means the executing process. Okay, the executing process, and then we have another process information and another process information here. So we have the currently run at here, and it will goes to this part, or it will goes to the next part. So the kernel maintain The kernel maintains a pointer to the current process of the system. So means here all the active processes represented by the task structure. Okay, these one are the processes, and we have the task structure. Okay, but the pointer is given to the active or the executing process. So based on that diagram, we have the task structure for the specified process. Okay, and then if we assume that the system would like to change the state from the process currently running to the value or to the new state. So if the current pointer is the process, and then the current pointer at the pointer at the executing process, so its state is changed with the current state equal to new state. Okay, it look like the statement if you want to do it in the operating system. So this just show you we have multiple processes. Okay, we have multiple processes, but the pointer will show or point to the process that being executed. So if we want to change from this current state to the next or new state, we just put current, the equal state here equal to new state. So it will change from this pointer to another process. Okay, that is how the process representation in Linux using the C structure. In the C structure, task underscore struct. Okay, this one. The task underscore struct. This one is under the C programming language. So the next point, we go for the scheduling. Scheduling is a process like we have a queue of many processes and which one should be executed first. So maximize the CPU use. Quickly switch process onto CPU for time sharing. Okay, this is why the process scheduling being there. Okay, because we want to maximize the CPU. Okay, process schedulers will select among the available processes for the next execution on the CPU. Just like when you print something, so your the first click on the print, it will queue, and then another job sent to the printer, so it will queue. After done one pages, it will print another pages, and it will print another pages based on the queue management on the system. So the same things goes for this here. We have the process scheduling. So process scheduler selects the processes that have that active in the current situation for the next execution on the CPU. So maintain the scheduling queues of the processes, the task of the scheduler. So we have the job queue because we have a queue of the processes. So job queue is set of all processes in the system. So the all processes need to queue. So we call as the job queue. Okay, next we have ready queue. Okay, so ready queue is referred to the set of all processes that residing in a main memory and ready and waiting to execute. You can recall back the state diagram. We have create, we have ready, but okay, so it's look like that part. We have job queue and then we have ready queue. So ready queue means it's ready and waiting to be executed. Okay, the next part we have the device queues. So this one is a set of processes that waiting for input or output device. Means it okay, let's say the process of printing something. So it's need to wait for the printer to send the instruction. Okay. And then processes migrate among the various queue. So these are about the process scheduling, and you should know what is the job queue, ready queue, device queue, and the process scheduler itself. Okay, this diagram show the process in various queue. So we have PCB 2, 3, 7, 6, 5, 14. Okay, this one is a PCB. So inside the PCB we have the registers. Okay, as the previous video we discussed about this part. And then we have the queue part. Okay, process queue. So header here, queue header, and then ready queue we have n. So it will queue for the execution process. Okay, in scheduling, the objective of multiprogramming is to have some process running at all time. Means every time there are process that running inside the CPU to maximize or utilize the CPU. So that the processes need to interact with each program. Okay, that's why we have the process scheduling. Okay, this diagram show the ready queue. Okay, at the left side, okay, you may look at of the ready queue and the various process at the right side. Okay, the PCB part. Okay, so when we have many process like this one, the process scheduler is responsible to select an available process for execution on the CPU. So for a single processor system, there will be never more than one running process in a time. So if there are more processes, so the rest will have to wait in the queue until the CPU is free and can be rescheduled. So that is the task for the process scheduler. In a system, we have many process, so they need to make a queue. So the process scheduler will select which process should be executed. Okay, that's the scenario that we can assume and imagine what will what happened inside the computer. Okay, this diagram show the representation in the process scheduling. So we have the queuing diagram that represent queues, resources, and flow. Okay, we have the ready queue. This one is CPU. This one is based on the input output request. And then we have the input output queue. Depends on the process. So this one is involve the scheduling queues. So scheduling queues is a process that enters to the system. Okay. Next is about the scheduler. Okay, we know about the process scheduler. So process scheduler will select the process that already ready for the next execution part. So the short-term scheduler or CPU scheduler select which process should be executed for the next and allocate it to the CPU. So sometimes the only scheduler in a system. Short-term scheduler is invoked frequently by the process. And long-term scheduler, okay, we have short-term, we have long-term. So the long-term is referred to job scheduler, short-term is referred to the CPU scheduler. So these are the difference. So this scheduler will select the processes should be brought into a ready queue. Okay, for the long-term scheduler is invoked infrequently compared to the short-term scheduler. Okay, the long-term scheduler control the degree of multi-programming. And processes can be described as either input-output bound process or CPU bound process. So input-output bound process, it spends more time doing the input and output than the computation, means the process in the computing system part. And many short CPU is CPU bound process spend more time doing the computations and few very long CPU bursts. So long-term schedulers strive for the good process mix. Next is the medium-term scheduler. We have short-term, long-term, medium-term. So this scheduler can be added if the degree of multiple programming needs to decrease. We want to decrease the level of multiple programming. So remove the process from the memory, store on the disk, and bring back it from the disk to continue the execution. This term we known as the swapping. Swap out, swap in. Okay, here we have the CPU, and then we have the process ready in the queue. In this one, waiting queue for the input output. Okay, after waiting, then already get the permission, then go to ready queue. Okay, this one partially executed swap out process, means ready, and then it's partially executed, and then it swap out the process, means goes to the CPU, swap out, and then swap in again. Okay, this one is the medium term scheduler. So it remove the process from the memory, store on the disk, and bring it back from the disk to continue the execution. So we call as the swapping. I mean the process already goes to the memory, and then because we want to decrease the multi-programming part, so it need to remove from this process, and then after swap out, and then it waiting for swap in again, and then it will continue with the execution. So this one is the medium term scheduler. Okay, when the CPU switch to another process, from one process to another process, the system must save the state of the old process and load the save state for the new process via a context switch. So context of a process represented in the PCB. Okay, you can refer to the slide 3.9. So context switch time is overheat, and the system does no useful work while switching. So the more complex of the operating system and the PCB, means the process block, the longer the context switch. So time dependent on hardware response is some hardware provide multiple set of the registers per CPUs and multiple context loaded at once. So depends on your hardware, either it provide the support or the capability or not. Okay, that's refer to the context switch. So it do the switch to the from one state to another. The next part we go to about the operation on the processes. Okay, based on the operation on the processes, we have two mechanisms: process creation and process termination. So process creation is referred to the new step to create a new process, and then terminate end of the process. Okay, parents process create the children processes. Okay, before this, in the example of the Linux, we know that we have the parents, we have the children, and we have the sibling. It look like a tree. Okay, parent process create the children processes. So it create other processes and forming a tree of processes. Okay, it look like you can imagine the organization chart. We have the top part, and then from the top we have the employees, from the manager, and then we have the employees. Okay, you have the parents and you have the children. It look like the tree diagram. So generally process identify and manage via the process identifier that we call as PID, process identifier, to identify what are the process. So resource sharing option, the parents and the children share all resources. Children, this one is referred to the process. Children share subsets of the parent resources, and parents and children share no resources. Okay, option for the resource sharing when we talk about the parents and the children processes. First, we have the parents and children share all the resources. Second, we have the option where the children share subset of the parents' resources. And third, we have the option where parents and children share no resources. Means they don't share the resources. That are the option when we talk about the parents and children in the process creation. Okay. In execution, we have two options. Parents and children execute concurrently. This one is referred to window NT. And parents wait until the children terminate, refer to the Unix. So this one is execution option. Means at this level, both process run simultaneously. And at this option, the parents need the children terminate the process, then the parents can continue. Okay, so this is the tree diagram. So a tree of the process representation in the Linux. Okay, we have the PID, process identifier. Okay, the initial part means when we create the process. So one, and then login, read, SSHD. So this is the children of process 1, children of process 1, children of process 1. Okay, and then these are the sibling. Okay, this one is the parents, children, parents, children, parents, children, parents, children. So this one parents, this one is children, this one is children, and this one is the sibling. So the option is based on this one. Okay, concurrently wait until the children terminate. So address space is allocation of the address. So children duplicate of the parents. Children has a program loaded into it. In the Unix example, we have the function fork and function execute. So fork function, system call create the new process. Exec function, system call use after a fork function to replace the process memory space with a new program. So it looks like this diagram. We have the fork function, we have the execute. So parents and children need to wait, execute. After execute, we can exit. So forks is create new process. Okay, execute means we execute the process. So the next process is termination. So in this process, process will execute last statement, means that termination is the last process for certain process. Okay, because it's end of the process. When process execute last statement and then ask the operating system to delete it using the exit function system call. Okay, so we have a fork, and then we have the exec, and then we have the exit. Okay, and then we also have the wait. So it returns status data from the children to the parents via wait function. So process resources are deallocated by the operating system. So operating system will allocate and deallocate the resources of each processes involved in the system. And parents may terminate the execution of the children processes using the abort function system call. So when and then some reason for doing the abort function or terminate during the execution process are children has exceeded the allocated resources. Second, task assigned to the children is no longer required. And third, the parent is exiting the operating system. The parent is exiting, and the operating system does not allow the children to continue because the parents already terminate the process. So if the parent already terminate the process, so the children process cannot be continued. So it also need to be terminated. Okay, some operating system do not allow the children to exist if its parent has terminated. So if process terminates, then all the children must also be terminated. Cascading terminated, all children, grandchildren, extra are terminated. Mean cascade everything. And the termination is initiated by the operating system based on the system call. Okay, the parents process may wait for termination of a children process by using the waiting system call, and the call returns status information and the PID or the process identifier of the terminated process. So it's look like this one. PID equal to wait status. How to assign the function to the process identifier. So if no parents waiting, means did not invoke wait function, process is a zombie. And if parent terminated without invoking wait, so process is and wins, mean tak ada ayah lah, tak ada parents. Okay, so that's all for the first part of chapter 3. So the last two process is about the process of creation and process of termination. So in this process of creation and termination, you should understand the system, the tree diagram about the parents and the children, and the process of execution and terminate. There are several options. and several function from the system call that being call for certain part. Okay, so that's all for the first part of chapter 3. So we will continue on the next session on the chapter 3. Okay, that's all. Thank you and assalamualaikum.